Sometimes we need to develop dynamical estimators that can give us aspects and informations that we're missing in our dynamical systems. So for example, if you have a specific type of sensor on your dynamical system and you're missing some sort of information, you can use the idea of Kalman filter and use a model of your dynamical system to estimate the information that you're missing. So suppose I have a plant, and what goes into my plant is some input noise and some input, and I have my output that I'm measuring, and there is a process noise that's added to my output. Then I can use the idea of a Kalman filter to estimate my output and to estimate the states of my system. That's shown by X bar and Y bar. So another example would be if I have a 3-story building, and for instance, I know what the accelerations are at each of the floors because I have accelerometers on each of the floors, but I don't really know what the displacements are. So this is another example where I can use the model of my system and the idea of Kalman filtering to be able to estimate the displacements that I have from the acceleration results that I have. And a typical input into the system is earthquakes. So it's a classic earthquake engineering problem. So what I can do in this example is to give my dynamical system, my building, some sort of input, in this case the earthquake, or any kind of, it could be wind, it could be any kind of excitation, and then I can use a Kalman filter, and I can use the Kalman filter to obtain and identify the results and the informations that I don't have. So I can give it all these acceleration informations, whatever I have, and I can withdraw displacement information, which I don't have. And very often we don't have any displacement transducers on buildings, so accelerometers are very commonly used sensing devices. So having said that, we can say these are estimated, and usually these estimates are pretty good for linear systems. If we are interested in nonlinear systems, we want to use unscented Kalman filters or even particle filters. And those are much more sophisticated and beyond the scope of this lecture. And that's just for you as a reference. So this is just a brief overview, and what we're going to do now is to develop the theoretical aspects of Kalman filter. And to do this, I want to start off by talking about a linear dynamical system, and this is a discrete system. And we've done this in the past where we've drawn the state space formulation for a linear dynamical system. And the discrete time system looks like this. It's written in terms of discrete time steps. So here x of t is not a continuous time step. These are discrete. So you can think of t as being 1, 2, 3. And the x value has some sort of expected value. It has a mean. And it also has a variance. And the variance, we can go back to our undergrad degrees, and this is what they look like. It's the expected value of the differences. As such, there's a transpose, and so I could do the same thing for my input u, find the mean for the input u, and find the variance for this u value. So these are important statistical relationships that we're going to use throughout this lecture. Now I'm going to take this dynamical system and I'm going to express it in terms of its mean values. So I have all these x bars and I have u bar. And I'm going to put a star here because this is a very important relationship. Now, what I'm going to do is I want to consider the variance of the system. So the very first thing that I want to do is I want to take my actual states, let's say at time t+1, and I'm going to subtract the mean value of the states from that. So in terms of the A and B matrices, this is the kind of relationship that I'm going to be looking at. Now, because this difference is happening at time t+1, when I take the variance, I'm also looking at the variance at time t+1. So if I want the variance of x at t+1, this is what I'm going to have. I'm going to have the expected value. That's what that double E means. And I will put what I had written in the first line here, and I'm going to multiply it by itself. So here it is. And this is really how we do covariance or variance. These are pretty much analogous. And once we do the arithmetics, we end up with these relationships. where we have sigma x, which is the variance of x, sigma u, variance of u, sigma xu, which is the covariance between x and u, and sigma ux, which is the covariance between u and x. As it turns out, so this is variance, covariance, and as it turns out, these two covariants are actually equivalent, so I can pretty much express one of them in terms of the other one transposed. And this is just a mathematical relationship that's pretty useful. In the case when x and u are uncorrelated, like there is no statistical relationship between the two, what we can say is that these sigma xu's and sigma ux's are zeros, so these are uncorrelated. And this equation simplifies to the following. So now there's only two terms on the right. So this is another very important relationship. I'm going to highlight this and leave it in red. We're putting a star right next to it. There it is. And so if I now assume that my A matrix is stable and that sigma u and sigma x are constants when we arrive at steady state formulation, I can further reduce the relationship and really simplify it and pretty much get rid of all the time terms because it's no longer evolving with time at the point of steady state. So this is what I'll end up with. Oops. And really the significance of this equation is that it is of a form we typically call Lyapunov. And Lyapunov equations have very mainstream, very easy to find solutions. And in fact, this is the relationship we have. And in fact, MATLAB can solve any kind of Lyapunov equation for you. There it is. Then we can solve using MATLAB. Now that we have a number of important relationships that are established, I want to talk about linear Gauss-Markov models, and I'll explain in a second what kind of assumptions make a linear system a Gauss-Markov model. Imagine we have a dynamical system where instead of the usual inputs we have noise, we have process noise going into the dynamical system, and this process noise is W, and the output has a measurement noise that's sort of added to it, and we describe it by the term V. And I can pretty much do the schematic of this where we have the system and it has these noises that are added to it. Here it is, and the output also has a noise added to it. That's measurement noise. So W and V. The actual input is 0 and the output is Y. So we call this process noise. It's kind of like the input process, and measurement noise, which is the output noise. What I'm going to do now is to describe a number of statistical assumptions that a Gauss-Markov model has. For one, X, W, V, and Y are considered to be jointly Gaussian and independent. In short, they are uncorrelated. And the values for W and V can be thought of as zero mean. So, excuse me, this is a W. So this is a zero mean process, and it has a variance that we describe via W. So I can do the same thing for V. It's a zero mean process. And this is equal to V. And also the expected value for the initial conditions are described as such, where we have a mean value and we also have a variance value for the initial condition. And this is how we always describe variance. Transpose equal to sigma naught. There it is. And really, the last step is the description of the Markov property, where we say that the current time step, the current state we're in, is only dependent on the previous time step and nothing beyond that. So this is really the mathematical expression that tells the story. and we call this the Markov property. At this point, we can say that because of the Gauss-Markov process or properties, the mean values satisfy the following relationship. So this is the state space formulation without the input, where we have some sort of initial condition. The actual solution, xt bar, can be described as follows. So this is what we're satisfying, and a to the power t is an exponential. And the variance satisfies the following relationship. This was one of these derivations we did earlier. We have sigma x, and it's also a function of time. So, again, I can say A is stable, and I have the steady state assumption, so I can get rid of the t plus 1. Here it is. We can take these relationships and we can also think of these as properties, and we can pretty much condition them on the observed outputs of our dynamical system. So these are not all the outputs, but observed outputs. And I'm introducing this new x hat term, which is pretty much described by the mean square error estimate of the x value based on the observed outputs. And these outputs are written as y0 through ys. These are the different discrete time steps. And so based on the outputs, so forth. And pretty much I can write the covariance for this. It's written as we've done before. And transposed, there it is. So we're going to organize this and move things up a little bit. All right, so before we move any further, I think we should explain and elaborate on this whole notion of conditionality and what we are trying to estimate. So if I have x hat and it's for time t given t, what we're trying to estimate is the current state based on current and past observed outputs. So based on current and past outputs. And I can write this differently as well. I can say x hat t plus 1 given t, and this is a prediction of the next state based on the current and past observed outputs as well. So based on current and past outputs. So that's really what that means, and we have this fundamental relationship that's based on the covariances between the states and the observed outputs, and these are written as follows. The second one, I think, is an inverse, so this is what I have, and I'll do a quick proof of this in the next slide, so I'll put in the star next to that. Okay, so for the proof, I'm going to say I have a linear system that can be described by z is equal to x1 plus ax2. And what I'm stating is that z and x2 are uncorrelated parameters. So if I were to do the covariance of z and x2, they should theoretically equal to 0. And I can pretty much expand as follows. And I know the first covariance is equal to sigma 1, 2. And I have a variance x2. I can pull the a out. And because this is equal to 0, a will have the following format. Now, this is the first part of the proof. And the second part is I need to do the following expected value where I have z minus ax2 given x2. And I can simply expand this. And so this is kind of simplified because now we know what the expected value of z is, and this can be written as follows: sigma 1, mu1 plus sigma 1, 2, sigma 2, 2 inverse, and so forth. And this is really a proof of that earlier relationship. Okay, so now that we have all these early proofs and statistical relationships out of the way, we want to dive right into the Kalman filter idea and to really explain what it is. And pretty much it's a method for computing the x hat t given t, or pretty much the states of my system recursively. And we can pretty much estimate the current time step and the future time step as a prediction. We're trying to do some sort of measurement updating so that we can have these statistical error estimates based on or in terms of the previous time steps. So based on x hat and sigma at t minus 1. And pretty much we start off with the output to this system, and we are going to condition the output at the current time step to all the outputs at previous time steps. So condition at y t minus 1. And so we have this conditionality statement, cxt given. And what you're noticing now is that v and y are uncorrelated, as we stated earlier, per the assumptions. So these are uncorrelated. So we can get rid of the second conditionality statement and just simplify this as follows, given y plus v. So there's v. It's not conditioned on y. So if I say that my states and my outputs are all conditioned on yt minus 1 and are all jointly Gaussian and uncorrelated, then I can do some sort of statistical analysis where I can find their means and covariance matrices. And if you forgot what a covariance matrix is, if I have two terms x1 and x2, I can always get the means. Means are mu's, and I can get the covariance matrix, which is the variance of x1, covariance between x1 and x2, same thing, and then variance of x2. This is what a covariance matrix is. Then I can draw some useful information like this for my states and output. So for my states I have the following, and for my output I have c multiplied by the states. And so the covariance matrix is as follows: C transposed. This one's the transpose of the original, and this is the last bit of information we need. Okay, so, and this is a matrix again. And so I can grab these mu's and sigmas and plug them to some of the equations some of the proofs we did earlier. And the first one is for t given t. So this is the error estimate of the states, and this is the relationship we obtain. Now, what I want you to look at is how the variable describing time t, given t, is conditioned, and it is pretty much dependent on t given t minus 1. So the current time step is all in terms of t minus 1. And I could do the same thing for the sigma or the variance. And again, we're seeing that the current time step is described by, on the right-hand side of the equation, by t minus 1, the previous time step. And this is really the idea of measurement updating when you think about it. So the previous time steps estimating the current time step. So these are important relationships, and we have t given t in terms of t given t minus 1. And this is really what measurement updating is. And another thing that we're doing is we are estimating xt based on measurements of y of t. So that's important as well. So once we're done with a single time step, we want a time update. We want to move on to the next time step. So we're done with t minus 1, we're done with t, we're going to t plus 1, and we're using t to give us information about t plus 1. And I can again condition on y of t, and w and y are independent, so w is not written given y, and so sigma t plus 1 given t can be simplified as follows. Okay, so we did all this math, and now we have the formulation for the Kalman filter. It is comprised of 2 steps. It has a measurement step and it has a time updating step, and together they give a recursive solution that we could use to estimate our states. The very first step for a Kalman filter is for us to know the initial conditions for the system, and we express these in a statistical sense as well. We have the mean values and the variance for the initial condition. And the second step is the measurement step that we sort of discovered earlier, where we have the error estimate and we have the sigma. And these are long equations, so we're just going to write them down. And don't be intimidated by these equations. We have a lot of software packages that can take care of the concept of Kalman filter. They could handle your filter for you. You don't have to do all these by hand. And we're doing this for sigma as well. So hopefully I've done these correctly. I do tend to make a lot of errors. Plus V. Okay. And step number 3 is the time updating step. And we take the dynamical system and calculate the state at t plus 1. And we do the same thing for the covariance or the variance. These are pretty much analogous. And we repeat. We do the same thing for time 1, and time 1 gives us time 2, and so forth. Okay, now bear with me, we're almost done. What I want to do now is to combine equation 2 and equations 3 together to give us a simplified Kalman filter equation. So this is the time updating step with the measurement equations embedded in it. Inverse, and the y value goes in there. So here we are. And what I can do is I can simplify this. I can package a lot of these variables and express them as L of t. And L is pretty much an observer gain. This was something we talked about in lecture 6. And observer gains are pretty important anytime we talk about estimators. So that's the observer gain, and that's the output prediction of output. And this here is the observer gain. And the last bit of simplification that I really want to do is for the steady state Kalman filter situation. And we take the expression that we had for sigma and get rid of the t variable because we're already at state space, steady state, and we don't need to evolve with time. So this is what I have. And this kind of equation is what we typically call algebraic Riccati equation, and this can be solved directly via MATLAB or any kind of any other software package, Python. And the major assumptions here are that the C and A combo are observable, and the A and W combo are also controllable. So those are important. And lastly, we call this algebraic Riccati equation. Okay, so now that we've covered the theoretical aspects of Kalman filter, let's get back to this 3-story building structure example that we talked about with the input earthquake force going into the building. And we can imagine that we have 3 accelerometers in each of the floors of this building, because usually that's how things work. We don't have displacement transducers those are very inconvenient, almost impossible to place in a building, we usually have accelerometers. And we basically want to use the acceleration data that we have from the 3 stories and the idea of a Kalman filter to be able to derive and estimate these displacements at each of the floors. And the biggest prerequisite to doing something like this is having a reasonable model of this 3-story building. And I'm going to assume in this example, I already have a reasonable model of this building. If you're wondering how we model dynamical systems, we've already made the videos on that, and those are posted in this lecture series as well. So here I have a MATLAB code. I'm loading the ground motion. I'm entering mass, stiffness, and damping values, and these are matrices because I have a 3 degree of freedom system. I am converting these matrices into state space formulation. There's a video on that as well if you haven't watched yet. And lastly, I have a model of this building structure. So what I do next is to use the Kalman filter option that MATLAB has. This is a command, Kalman, and I enter the model of the building structure, assuming that the only inputs I have into my Kalman filter are my acceleration. So the only thing, the only knowledge of this building I have are the acceleration results. And from the acceleration, I want to pretty much estimate what the displacements are via Kalman filter. So I design it as such. There needs to be some scaling that I'm doing here. And then I open MATLAB, and here it is. So I have an input ground motion going into my building model, and my building model is feeding its acceleration results to Kalman filter. I'm also adding some noise to my measured results because measurements always have noise for one reason or another. And you're seeing the ratio between the noise and the actual measured signal. So you can tell the noise is quite substantial. And lastly, this acceleration result goes into a Kalman filter, and I am going to compare my estimated displacements and accelerations to my real displacements and accelerations. So if I look at displacement for floor 1, this is what I have. The blue is the estimate and the yellow is the real displacement. I gotta zoom in a little bit for us to be able to see both of them together. And there they are. You can kind of tell that the estimated has noise in it. That's very much aligned with what we see in reality from real structures. There's always noise, and that comes with sensor use and accelerometers and so forth. So these are displacements for floor 1, displacement for floor 2, and we can tell there's a good match between the estimate and the actual real theoretical value of the displacement. And of course, accelerations should match as well because the accelerations were inputs into the Kalman filter. And they're quite noisy just because of the scale of the noise that we added to this problem. Okay, so again, the idea of Kalman filter is I have a credible model of my dynamical system. I'm missing a number of states, or I'm missing a particular output. I use what information I have to be able to draw all those information that I'm missing. And for that to be true, the system has to be observable, controllable, and so forth. All right, I'll see you next time.